Welcome to the video lecture on the subject Computer Vision. Unit 4 3D Reconstruction Part 4 video. I am Dr. K. Padmapriya, Assistant Professor, Department of ECE, Government College of Engineering, Tirunelveli. Facial modeling and tracking. Another area in which the specialized shape and appearance models are extremely helpful is in the modeling of heads and faces. Even though the appearance of people seems at first glance to be infinitely variable, the actual shape of a person's head and face can be described reasonably well using a few dozen of parameters. In figure, it shows an example of an image-based modeling system, where the user-specified key points in several images are used to fit a generic head model to a person's face. It shows the 3D model fitting to a collection of images where these 5 images, it is along with the user's selected key points along these poses, different poses of a face, and the complete set of key points and the curves, and these are the 3 meshes, the original and the adapted after adding up the adaptation with these 13 key points and after adding some 99 key points. And this shows the partition of the image into separately animatable regions. And it's after specifying just over 100 key points, the shape of the face has become quite adapted and recognizable. Extracting a texture map from the original images and then applying it to the head model results in an animatable model with striking visual fidelity. The head and expression tracking and reanimation using deformable 3D models. Models fitted directly to 5 input video streams, and the bottom row, it shows the results of reanimating a synthetic texture mapped 3D model with pose and expression parameters, and this shows the model fitted to the frame rate space-time stereo surface models. And here these all shows is the green markers overlaid and all the green dots, while the bottom row, it shows the fitted 3D surface model. A more powerful system can be built by applying principal component analysis to a collection of 3D scanned faces. It is possible to fit morphable 3D models to single images and to use such models for a variety of animation and visual effects. Stereo matching algorithms optimize directly for the head model parameters or to use the output of real-time stereo with active illumination. Modern systems can capture these in real time, and not only the surface details such as wrinkles and creases, but also the accurate models of skin reflection, translucency and subsurface scattering. A 3D head model can be used in a variety of applications such as head tracking and face transfer, that is, replacing one person's face with another in a video. Face beautification by wrapping faces images toward a more attractive standard face de-identification for privacy protection and face swapping. In all these applications, this 3D head models are used. So 3D morphable faces. So here it shows the original 3D face model with the addition of shape and texture variations in specific directions. And the deviation from the mean caricature, then for gender expressions, then different expressions, weight, and the nose shape, everything could be changed in this morphable faces. And the part B shows the 3D morphable model which is fitted into a single image, after which its weight or expression can be manipulated. It shows another example of 3D reconstruction, which is the original image and then initially changed, and after each steps it's been mentioned with the result, and then the final 3D reconstruction and the manipulations made like lighting, poses, changes in those poses, etc. And here it shows the timeline of 20 years of 3D morphable head models, including the results from the actual paper, and it is first publicly available morphable model and facial reenactment results and GAN-based models. Application: facial animation. Most widely used application of 3D head modeling is facial animation. Once the parameterized 3D model of the shape and appearance, that is the surface structure, surface texture of a person's head has been reconstructed. It can be used directly to track a person's facial motions and to animate a different character with these same motions and expressions. The resulting texture mapped 3D model can then be modified to produce a variety of visual effects, including changing a person's weight or expression, or the 3D effects such as relighting, changing the position or location of the lighting, or 3D video based animation. Such models are used for video compression by only transmitting a small number of facial expression and pose parameters to drive a synthetic avatar or to bring a still portrait image to life. 3D facial animation is often matched to the performance of an actor in what is known as performance-driven animation. Traditional performance-driven animation systems use marker-based motion capture, while some newer systems use depth cameras or regular video to control the animation. Contour uses a combination of phosphorescent paint and multiple high-resolution video cameras to capture real-time 3D range scans of the actor. These 3D models were then translated into facial action coding system, which is FACS, shape and expression parameters to drive a different synthetically animated computer generated imagery character, that is a CGI character. So computer generated imaginary character is a CGI character. Human body modeling and tracking. Tracking humans, modeling their shape and appearance and recognizing their activities are some of the mostly actively studied areas of computer vision. Certain survey performs initialization tracking, which includes background modeling and segmentation, pose estimation and action recognition. Certain survey performs sections on tracking, background subtraction, deformable templates, flow and probabilistic models recovering 3D pose from the 2D observations, and data association and body parts motion synthesis. Different areas are background subtraction, initialization and detection, tracking with flow, 3D kinematic models, probabilistic models, adaptive shape modeling and activity recognition. Background subtraction. One of the first steps in many human tracking systems is to model the background to extract the moving foreground objects, which is also called as silhouettes, corresponding to the people. Difference mating and background maintenance modeling techniques and techniques based on mixture models, comprehensive modeling of the background image statistics and appearance of the foreground objects, example their edge and motion statistics. Silhouettes have been extracted from one or more cameras and are modeled using deformable templates or other contour models. Tracking such silhouettes over time supports the analysis of multiple people moving around a scene, building shape, and appearance models and detecting if they are carrying objects. The next step is initialization and detection. So to track people in a fully automated manner, first detect their presence in individual video frames, which closely related to pedestrian detection, which is often considered as a kind of object recognition. Techniques for initializing 3D trackers based on 2D images. Single frame human detection and pose estimation algorithms can be used by themselves to perform tracking. Frame to frame tracking techniques are used to provide better reliability. Tracking with flow. The tracking of people and their pose from frame to frame can be enhanced by computing optical flow or matching the appearance of their limbs from one frame to another. For example, the cardboard people model models the appearance of each leg portion, upper and lower, as a moving rectangle and uses optical flow to estimate their location in each subsequent frame. Tracking limbs using optical flow and templates along with techniques for dealing with multiple hypotheses and uncertainty for 3D model of limb and body motion. Match the estimated motion field itself to some prototypes in order to identify the particular phase of a running motion or to match to low resolution video portions to perform video replacement. Flow-based tracking is used to track non-rigidly deforming objects like t-shirts, etc. Use the interframe motion to estimate an evolving textured 3D mesh model of a moving person. 3D kinematic models. The effectiveness of human modeling and tracking can be greatly enhanced using a more accurate 3D model of a person's shape and motion. Underlying such representations, we are ubiquitous in 3D computer animation in games and special effects. It's a kinematic model or a kinematic chain which specifies the length of each limb in a skeleton as well as the 2D or 3D rotation angles between the limbs or segments. Inferring the values of the joint angles from the location of the visible surface points is called inverse kinematics, IK, and is widely studied in computer graphics. The figure shows the tracking of 3D human motion. So in part A, a kinematic chain model for a human hand and the angles and the representations of them. And here it shows the tracking of a kinematic chain blob model in a video sequence. It shows the probabilistic loose-limbed collection of body parts. So as time varies, how it is changing over. It shows a kinematic model for a human hand used by the persons to track a hand motion in a video. The attachment points between the fingers and the thumb have 2 degrees of freedom while the finger joints themselves have only 1. Using this kind of model can greatly enhance the ability of an edge-based tracker to cope with rapid motion, ambiguities in 3D pose and partial occlusions. In reliable real-time hand tracking and modeling, the Kinect consumer RGB camera was used, and regular RGB tracking and modeling has also improved with using neural networks for reliability and speed. Several systems combine body and hand tracking to more accurately capture human expressions and activities. In addition to hands, kinematic chain models are even more widely used for whole body modeling and tracking. In addition to hands, the kinematic chain models are even more widely used for whole body modeling and tracking. An ellipsoid or superquadric is associated with each rigid limb in the kinematic model as shown in the figure. This model can then be fitted to each frame in one or more video streams either by matching silhouettes extracted from known backgrounds or by matching and tracking the locations of occluding edges. In real-time skeletal tracking, the Kinect consumer depth camera was used for interactive video game control as shown in figure 13.28. In skeletal tracking, some techniques use 2D models coupled to 2D measurements, and some of them use 3D measurements like range data or multi-view videos. Use these 3D measurements with 3D models, and some other techniques use the monocular video to infer and track the 3D models directly. So this is a depth image. From that it is inferred body parts and hypothesized joints, and this is the tracked skeleton. So it shows the Kinect skeletal tracking pipeline, which consists of per pixel body part classification, body joint hypothesis, and then mapping to a skeleton using temporal continuity and prior knowledge. Usage of temporal models to improve the tracking of periodic motions such as walking by analyzing the joint angles as functions of time. The generality and applicability of such techniques can be improved by learning typical motion patterns using principal component analysis. This is the end of your part 4 video.